continue to talk about segment trees. This is, again, if you watched the lesson on code forces you do section, the first part of the lecture will be exactly the same as in the second lesson about segment trees. Let's go. Let's remember what we did last time. So we have the segment trees and trees. So last week we discussed the following data structure. We have the array, and we have two types of queries. First query is to change the element, so we have something like set element I to v, and the second query is to find like sum on the segment or minimum on the segment or any other associative function on the segment. Sum. And we discussed how to make the segment tree in such a way that both these operations work in log time. So we have both these operations in log n time. Cool. Now, today we will use again segment trees, but we will try to handle different type of operations. Today we will handle two types of operations. First operation will be to change the whole segment of elements. So we will change, let's say we will add to some elements. So we will add from L to R value v. So we will change the segment from L to R by adding the value v to all elements on this segment. So we'll make AI plus equal v for all I from L to R minus 1. Now, the second operation will be to get the current value of the element. So let's say we have get. I will simply return element in position I. That's the plan for today. Now again, if you have simple array, if you just have an array, then you can make this query in constant time. But for this array, you need to iterate over all elements of this segment, so it will cost you linear time. So we kind of want to make this operation faster. So we want to make an operation which adds something to all elements on a segment faster than just iterating over all elements of this segment. And by doing this, we also want to be able to get the current value in each element in some good time. We'll do it both operations in log n time actually. Do we have OnlyFans? Not yet. Who knows? Now, let's go. So how to make both these operations works in log n time? We will kind of build this segment tree like in previous lecture. So let's build segment tree of like 8 elements. 8 elements. Oh. I used almost all the board. Okay, I'll try it. Now we will build a segment tree. The structure of segment tree is always the same. So we'll just make a full binary tree when these elements are the leaves of this binary tree. So we'll make one element here, and so on. And now all elements of this tree just empty, all contain zeros. So now, what will be the meaning of all these nodes? Like before, each element corresponds to some segment of the array. Like for example, this element corresponds to this segment, and this element corresponds to this segment, and so on. So each node of the segment tree corresponds to some segment of your array. And the numbers we will put in these nodes will correspond to the numbers which we should add to this segment. So if we have some number in this node, it means we should add this number to all segments corresponding to this node. That's all. Now, how to make both these operations? It's pretty simple. So you have some segment. Let's write some segment. We have segment. I always use the same segment, so okay. This is just a good segment. It has 3 parts, so it's kind of a good example, but we used the same segment on the previous lecture. Okay, so let's have some segment and try to add some number to this segment. Let's add something 5 to all elements of this segment. How can we make this operation using this segment tree? We will split this segment into some parts such that each part is contained in some node of this segment tree. Like in previous lecture, again, we have this segment. We can split it in this segment, which is in this node, this segment in this node, and this small segment in this node. So if we want to add number 5 to all elements of this big segment, we will add it to these 3 small segments. So we'll put 5 here, 5 here, and 5 here. That's all. That's how you add something to the whole segment. You split your segment into some parts, add 5 to all these parts, and so you have all elements increased by 5. Okay, so how to find these nodes? So how to find all the nodes which combines in your given segment? Well, exactly like we did on the previous lecture. So in the previous lecture, we need to split the segment in some parts to calculate this sum. Yeah. So if you was in the previous lecture, I hope you kind of remember what's going on. Now we need to do the same thing, but instead of calculating the sum, we will just put this v in these nodes. So again, we will make the recursive function. It will start from the root, and each time it will recursively call from the left tree and from the right tree. And we have the same 2 cases when we stop the recursion. So we go left to go. Here we stop the recursion because this segment doesn't contain any interesting elements. So we check this node. This node represents this segment of the array. This segment contains no element of the segment we need. So we stop the recursion here and go back. And when we go to the right, this segment is completely inside our segment. So when this segment is completely inside, we just put our number here and also stop the recursion here. So we go here, see what it is inside, add 5 to this node, stop the recursion, go back, here, go here, go to the left. This segment is completely inside, so we add 5 here, stop the recursion, go back, go here, add 5, stop the recursion, go here, stop the recursion. So the procedure is exactly the same as on the previous lecture. Sorry, I know I dropped the markers right near the microphone, so maybe okay. I believe I used to have a separate table for my markers, but I kind of moved it, so sorry, technical difficulties. Now let's write the pseudocode just to make it perfectly clear. We make a recursive procedure. Again, we add this LRV, and we add 3 parameters like before, like the current node and the borders of the current node. And now we make the same 2 checks. First, we check if the segment is completely outside. So if it is Lx greater or equal than R, or if Rx greater, if L is greater or equal than Rx. And then we're completely outside. If we're completely outside, we just return. If we are completely inside, L and Rx is also equal to R. Then we add this value v to the current node. Let's see, 3 v plus equal 3x plus equal v, and return. If none of this, then we make two recursive calls like before. It's exactly like before. This whole code is exactly like before. We make m equal to rx plus rx over 2 and make two recursive calls. Left subtree and right subtree. M. That's all. And this code works also in logarithmic time exactly by the same reasons like we discussed in the previous lecture. So the total number of nodes we visit in this recursion is up to log n. So this n works in log n time. And now to the second function. Now we need to find the current value of the node. So how to find the current value of, no, let's make some more operations just to make the tree more interesting. So let's add something to something. Well, let's have something small. Let's add 1 to this small segment. So when we add 1 to this small segment, we make the same recursion. So we start in root, go to the left, go to the left, go to the left, stop the recursion, go to the right, stop the recursion, add 1 to this node. Then we go back, go to this subtree, add 1 here. And let's add something else, just to make it more fun. Let's say, for example, for this, so let's have this segment. Again, we split each segment. This segment is split like this. So again, here we start the recursion, go to the left. This left subtree is completely inside, so we just add. Add what? I need some number. 2. So let's add 2 to this segment. So we go to the left subtree. This segment is completely inside, so we add 2 to this subtree. Then go here, go to the left subtree. Here we need to add 2, and we already have 5 here, so we add 5 and then add 2. It is the same as add 7 to the whole segment. So we need to take all elements on the segment, add 5 to all of them, and then add 2. It is the same as add 7 to all elements of the segment. So we just increase this 5 to 7. Cool. And now let's go to the second function. In the second function, we need to find the current value of some element of the array. So how to find how to find the current value of the element? It's quite simple. So we take some element. If we need to find current value, we just need to apply all the operations to this element. So we just follow the path from this root from this node to the root, and apply all operations on this path. So we apply all these operations to this node and find the final value of this element. So final value will be like 5 plus 2. It's 7. Arithmetics is complicated. So we will get of 3. That's all. That's how it went. And this operation also works in logarithmic time by just, it's obvious. Okay. So now we have both this operation works in log n time. I'm not playing guitar today. I don't usually play guitar. Sometimes I play balalaika, but it's before the lecture. Just ask me before the lecture next time, okay? Sorry. I don't play balalaika during the lecture. It's kind of killing the vibes of the lecture. So I'm trying to keep everything serious. I'm very serious. Why are we adding 5 only once? What do you mean? Oh, that's good reactions. Why do you mean only once? We have one operation plus 5, so we apply operation 5 only once. So for each element on this segment, we should apply operation plus 5. Yeah? Only once. When we add element to all segment, we add 2 elements in this. Sorry. When we had elements, we added number of elements in the segment tree times. What? No, we added only once. So this operation just increases all the elements on this segment by v. What? Let's say there is 2, 4, then the node current to 4 should be added 10. Why 10? You mean this node? No, this node just contains the operation. It doesn't contain the sum of all operations. No, we will go to this later. Now it's you're moving too fast. No, no. That's what we do. We just maintain the operations. So we have this operation plus 5, and we need to apply this operation plus 5 to all segments, to all elements of this segment. We don't try to calculate the sum on a segment and so on. We will do it later, but not now. By now, we just want to find the current value of this element. And to find the current value of this element, we just add all operations. So we go up to the root and find all operations which should be applied to this element. Okay. We will talk about lazy propagation just in a few minutes. Be patient. Okay. Now, before we go to lazy propagation, let's stop here for a few seconds. What I want to do is, again, I want to try to apply different operations. So we just create some segment tree for some operation, for this operation plus. So in this function, I apply operation plus to all elements of the segment. And sometimes you want to apply some different operation. So sometimes you want to have something like modify from L to R with parameter b. So you apply some operation with parameter b. So you have something like AI, and then you have some, again, we need some special sign for this operation. Let's have a star also. So this is some special operation. So we just apply this operation to all elements of the segment. Now let's think about what properties do we need from this operation to make this work. So if we just change, so I want what I want to do. I want to change this operation here, and also change this operation when I calculate the result. So when I calculate the result, this gets. Get is simple. So in get you make this recursive call. You add this x, L x, and R x. you make this recursive call like a to x plus 1 and so on. And then in the end you return s plus 3 of x. So I want to change this plus with this abstract operation, here and here. And I want to understand what types of operations actually works. So I want to find the properties of the operations we need to take care about when we try to make segment tree with this operation. Let's go. So let's think about what's going on when we apply the operation. We used several properties of the plus operation when we make this algorithm. The first property is pretty simple. When we let's see what happens to this node. Why we have 7 here? Because we add 5 and then add 2, right? So when we have some element, we apply operation plus 5, yeah, and then apply operation plus 2. So it's supposed to be working like this, yeah. But I put 7 here because this sum is the same as if we add sum of 5 plus 2. And that's the property we discussed in previous lecture. It's just associativity. So if we want some operation to be working in this algorithm, we need this operation to be associative, like before. Again, what associativity gives you for these algorithms? It gives you the opportunity to change 2 separate operations into like one big operation. That's why associativity is working. Because if you have some element, you apply one operation, then apply second operation. Let me just rewrite it. Let me rewrite it like this. So I want the following property. So if I have some element, I apply operation x and then apply operation y. So I have it like this. I should be able to change these 2 operations with some mega operation, right? So I want to make some combination of 2 operations to be the operation of the same type. Okay. So I want to change these 2 operations with one operation. And that's associativity. In practice, sometimes you have some strange cases. So in practice, sometimes you have like different operations here. So you have some operation which you apply to the element, and you have some different operation which gets you the combination of 2 operations. So sometimes here you have different operation. It doesn't matter a lot, but you always can change the operations in such a way that you have the single operation to all these cases. Like you have the single operation. When you apply it to element and operation, you have the result of operation. When you apply it to 2 operations, you have combination of these operations. So just for simplicity, you can see you can think about it like you have only one operation. In practice, sometimes when you implement this operation, you kind of have 2 cases. When you apply operation to element and when you combine 2 operations. So sometimes when you implement this operation, you have this if. So if you have this case or this case, it's not a big deal. Okay. Yeah. Good. Now, the second property we used. The second property of the sum we used is here. So when we try to calculate, let's try to calculate the final value of this element. So when we calculate final value of this element, we do it like this. We apply all operations to this element. So final value of this element will be 1 plus 5 plus 2 equal to 8. And that's not what actually happened to this node. Actually, to this node happened the following. We had this node, we first add 5, then we add 1, and then we add 2. And for plus operation, it doesn't matter, because plus operation is commutative. Yeah. Since this plus operation is commutative, so you can change the order of the operations. So we don't care about what is the order of operations. We just have all these operations in some order. We apply them in any order, and we have the same result in the end. That's because plus is associative. Okay, so Fenwick tree is better. We will talk about Fenwick trees next week. Let's go. So we need following property. First we need this operation is associative, and then we need commutative. And commutativity is not that common property. There are a lot of operations which are associative but not commutative. For example, if you multiplicate like matrices, so if you have some matrices in all these elements and you want to multiply the elements by some matrix, then the multiplication of matrices is not commutative, so it's not working. The simplest operation, which is not commutative but is associative, is of course it is just how it's called. Basically, the set operation. So when you let's call it assign operation. So when you assign value to some element, I don't know the good term in English. So simplest operation is basically assign value to the element. It's pretty simple operation. Yes, if you have x, you assign value y, you will get y. So it's quite simple operation. It's obviously associative. If you assign several values, if you assign x and then assign y, it is the same as assign x, assign y, and so this will be equal to y, this will be equal to y, and this will be equal to y. So it's obviously associative, but it is not commutative. If you assign x then assign y, it's not the same if you assign in the different order. So and this is actually quite common operation. So when you want to have operation like set, if you apply this operation here, you will have some things. You will have set from LB, which simply sets all values to V on this segment. Quite useful operation, and it is not associative. So it's not commutative. So we cannot assign values in different order. We'll get the different final result. So how to get rid of this commutative property? It's actually possible. So we can modify our algorithm in such a way that we don't actually need this commutativity property. How do you do it? You can do it. You do it in a way. So to get rid of this commutativity, we need to remember the order of operations. Like we need in this tree, we just forgot about the order of operations. We just put these elements in some order. So for each element, we don't know the order of these operations. Yeah, yes. I believe you can Google the good definition of associativity and commutativity. Okay. It's not about terminology, right? It's more about algorithms. So I think it's quite clear. So now, how do you remember the order of operations? Very simple way. We will remember this order of operations in this tree. like this. So when we have some element, we will apply all the operations to these elements from bottom to up. So if you have some leaf here, then you have the path from this leaf to the root. So this is the root. You have some operations in this node. The order of these operations is from bottom to top. So here we have some old operations, and here we have some new operations. That's the plan. We will maintain the following invariant. I'm trying to speak in more mathematical terms, but that's just to scare it. So we'll do the following. We'll always keep the things in such a way that for each node, all operations that should be applied to this node are sorted from bottom to top. So here in the bottom are the oldest operations, and here in the root are the newest operations. So when you try to calculate the value of this node, you just go from bottom to top like we did here. Here in this recursion, we calculate from bottom to top. So we recursively calculate the value in the child and then apply the operation in our current node. That's the plan. That's the plan. Now, how to maintain things in this order? Sometimes we will have some problems maintaining it. For example, you have some operation here. So you have some operation here. So for this node, you need to apply operation like plus x. I will just write plus just for simplicity, because plus is like more common than this. Well, okay, let's have this star. I just don't like to draw a lot of stars. It looks strange. So we have this operation which should be applied to this element. And then we have another query. So we need to modify some segment which contain this element as well. So we have some operation like this. So we have some operation. We need to apply value y to this segment. So we start the same recursive function. We start from the root, go somewhere, and we need to put y here. If we put y here, then the order of operation is changed. Yeah. So when we try to calculate this value, we first apply y and then apply x, and we want to first apply x and then apply y. So how we'll fix this? Very simple way. We will try to move elements deeper in the tree. So we will try to move these operations deeper in the tree in such a way that all operations will at some point go to the leaves of this tree. And this technique is called lazy propagation. It is lazy because we move operations down to the tree only when we need to. So when you have some operation which, like here, when some operation in your tree just when you need to add some operation below this current operation, only in this case you move this operation down in the tree. How to do it? It's quite simple. How to update on this side element, but not middle ones. Yeah. I'm not sure what you're talking about. So sorry. If you have any question, just give it some short explanation about the question. If you have only short question, I'm not sure what I'm talking about. I kind of lost the context. Go. So how to move operations down to the tree? It's pretty easy. So we have some node. In this node you have some operation. This node has some children. And you have some operation here and some operation here. What does it mean? It means that for all elements in this segment, you need to apply y and then apply x. And for all elements in this segment, you need to apply z and then apply x. Yeah? So what we'll do, we will move this x to both children. So we'll move it to the left child. In the left child, we need to apply x and then apply apply y and then apply x. It is the same as just apply the sum of y and x. So just to get the combination of these two operations and put it in this node. And the same here. Here we just apply the combination of z and y. And then we can remove x from this element. I mean, lose population, but I want some specific node to update in constant time. I'm still not sure what we're talking about. This operation works in constant time. I assume that I can calculate the result of operation in constant time. So this propagation in one node is working in constant time. I just remove operation from here, apply it here and here. So I have constant number of operations. Now, what's going on here? Here, I run the same recursive procedures here. So I start the recursion from the root, then go here. Then at this point, I need to go deeper to the tree. So I want to apply y to one of the children of this node, to the left child, for example. And I also have some right child here. So in this node x, I want to go to the left child of this element. So what I will do, I will propagate this operation x to both children of this element. So I propagate x to the left child, I propagate x to the right child, and remove it from this node. And now I go to the left child here, and I want to go even deeper. So I don't have this. I want to add y here, but not yet. So I go to this left child, and again I want to go even deeper. So I need to propagate this value from this node. So I take this node, apply the same propagation. So I move this x here, move this x here, and go deeper in the recursion, go here. And here I stop the recursion because I want to apply y to the whole segment. So I just apply y to this segment by adding it to x and y. And that's all. So every time you want to go deeper in the recursion, you just call this propagation and move the operation from your node to both children. And when you stop the recursion, just apply your operation to the current element. Well, let's change what will be changed. So we need to add propagations here. So this operation propagate will do this. It will take the current element, take both children, apply this x to both children, and remove it from this node. Let's say I want 5 elements to update, but any randomly, and each operation take constant time. Okay, let me read again. Let's say I want 5 elements to update. Okay, but any randomly. What do you mean randomly? Not in a segment, but some elements of the array. Not a segment, but some random elements. Okay. Yes, you can do it. No. One of the reasons you cannot do it, because to update n random elements, you need to read n random indices. So how do you describe n random elements when you in constant amount of memory. So, like to describe n elements, you kind of need n integers of indices just, and so it will be strange if you can do it faster than n log n. So if you just change some random elements, you cannot do it faster than just reading all the indices of these elements. So you can do it faster than linear time. Yes, this stuff only works on segments. This is why it's segment tree. Fortunately, there are a lot of different situations when you need to work with segments. So in various different situations, when you, like in various different problems, when you look on the elements we need to change, they form some segments. Sometimes it's going from, like for the chemistry problem, so you have just from monotonicity of something. You have something is monotonic. So if you just look on the set of elements you need to change, they form some segment of this array. Not always, but sometimes it works. So if it's not working, then you have some problem. X is the old operation, yes. Then x is the old operation, so x was here, and then we apply y to this node. So we need to apply x and then apply y, and that was happening. So now for this node, when we try to apply all operations from bottom to up, then we go from bottom to up. We apply all these operations, some even older operations. Then go to this node, apply x, then apply y, and then go up here. There are no operations. So we apply x, and then this y will be the last operation applied to this node. Cool. Cool. Ух ты. We spent an hour on this. Okay. It's a little bit slower than I expected. Okay, but that's good. But we discussed everything quite well. So I hope now it must be absolutely clear. In the lazy operation, y is y before x. No, these are different y's than x. No, okay, I have these two pictures nearby, but they're different pictures. I have different x, y here, different x, y here. Here I have situation, I have first way, I have this y and z. They are deeper in the tree, so I first apply operations from bottom to up. So first apply this y, then apply x. And in this picture I have, here I have y and here I have x. So there are different y's and x's in these two pictures. Okay, so here I apply x and y, and here I apply y. So I should use different letters for this, but okay. Now, no, implementation is very simple. No. You don't. If your implementation is hard, you're doing something wrong. This is basically the whole implementation. So this is the whole implementation of this end function, and this propagation is a very simple function. So when you call propagate, you simply take this value from here and apply it to both children. So you just take this to x plus 1, update it with value of 3x. You take the second child, apply value 3x, and then remove it from this node. No. It's very simple. It's nothing. There's no place in this algorithm which is kind of hard to implement. No. So that's basically the whole code. Now, let's move next. Now we will make things a little bit more complicated. So we will try to merge these two data structures. So first we build a data structure which can calculate sum on the segment, and here we make the data structure which modifies the segment. Yeah? Now we'll we'll try to make both. We'll try to make data structure which allows you to change the whole segment and find the function in the whole segment. I need to erase something. For example, let's make data structure which have two operations. First operation is to change the segment, like let's have add. We'll add value from L to R value. So again, it will add value V to all elements from L to R minus 1. And the second operation, let's say we calculate the minimum on the segment. So calculate minimum on the segment from L to R. Like this. So we'll try to merge the techniques from previous lecture when we calculated this minimum and technique from this lecture when we add element to the segment. Let's go. So how to merge these two techniques? Very simple way. We'll just take both these techniques and apply them in the same time. So we will build the segment tree. In each element, we will maintain two values. Well, let's build some segment tree again. Let's have some values. Let's have 2, 5, 6, 1, 4, 3, 7, 4. So we have this array. Let's build a segment. So we need to calculate minimums. So let's build a segment tree for minimum operation. So that's the simple segment tree for minimum. Yeah. This is a simple segment tree you use when you try to calculate the minimums on a segment. Now, you want to be able to add values to some segments. So we will maintain the same thing as before. So for each node, we will maintain another value, which is the value we need to add to this segment. So these values are the minimums, and we need another value, which is the value we need to add to this segment. Again, let's perform the same operation. So let's take this segment, make plus 5 to this segment. So what happens when we add 5 to this segment? Again, we will find the same three nodes and try to add 5 to this segment. So we add 5 here, plus 5 here, and plus 5 here. Now, when you apply the operation, you need to recalculate the minimums. Yeah. So after this operation, you want to again to be able to calculate minimums, but all these minimums are wrong. So you need to kind of change all the minimums here, right? What we'll do? We will recalculate the minimums, but not all minimums here, because there are too many elements here. So you can need to change all these minimums. We can't all change all these minimums. There are too many of them. So we will change only the minimums which are above these changed elements in the segment tree. So we will recalculate these elements. Let me show you. So we recalculate these minimums. So here, how to calculate minimum? So you have the previous minimum. Yeah, you have minimum on this segment is 1. Yeah? Now you add 5 to all elements of the segment. So the new minimum will be 6. Again, you have some segment. The minimum, you know the minimum on this segment. It is 1. So if you make plus 5 to all elements of the segment, they all change by the same value. So minimum is minimum. Yeah, minimum will stay the same. So this element again will be the minimum on this segment, but the value of the minimum will be increased by 5. So the new minimum on this segment is 6. 6. Cool. And also change these elements. So here will be 8, and here it will be 12. And now we'll recalculate the minimums above these elements. So to keep it like correct segment tree for minimums. So we'll go here, recalculate this minimum, it will be 2, go here, here minimum will be 4, this minimum will be minimum of 8 and 4, it's 4, and this minimum will be 2. That's all. So we recalculate these elements and all elements above these elements. Can we merge two or more segment trees? What do you mean by merge? Sometimes you can, but when you make some specific operation, usually the answer is sometimes you can, sometimes you don't. It depends on what actually do you mean by this operation. This we discuss only all the basic operations. If you want to some special operation, you need to think: is it possible or not? Sometimes it's possible, sometimes not. Sometimes you can prove that you can do it operation just because you will make certain algorithms, okay? For example. Now, so let's see. Let's see. So this is the segment tree for these two operations. So operation add to the segment and find the minimum. Let's see what's going on here. So what are these minimums for? These minimums are the minimums on this segment which don't take into consideration all the operations above this segment. So in some node, so there is some node x, yeah. In this node, you maintain the minimum on this segment, but without all the operations above. So above this element, you have some more operations here. And this minimum do not include these operations above this x. So here you have minimum without operations above. For example, let's add something more. So let's add something. What segment do you like? Well, let's add to something like, let's to this segment, let's add 3. So what will change? Again, you start from the root, make the same recursive procedure, and so on. Make the same recursive procedure as here. So you go to left, to left, to left. Go find this node. Add 3 here. When you return from the recursion, you recalculate the minimum. So this new minimum will be 5 plus 3 is very difficult. Will be 8. Then you go back from the recursion, recalculate this minimum. It is 2. Go back from the recursion, go here. Here you apply operation plus 3. So here you have plus 8. Apply this operation to this node. 9. I can do it. So it's 6 plus 3 is now 9. You go back from the recursion, recalculate this minimum as 2. Then go back, go here. Yeah, this segment is completely inside, so we just apply operation here. Here we have plus 3. Change the minimum to 7. Then go back, recalculate this minimum, it's 4. So that's all. Now let's see again. This minimum is 8, yeah, because it only uses this pressure. So this minimum is minimum on this segment without this operation plus 3. So the real minimum on this segment is actually 11. Yeah, because we need to all its elements we need to add 5 and then add 3. So this element is actually 11. Yeah, we added it was 3, we added 5 and then added 3. So this but this minimum is 8 because this minimum doesn't know about this element, this operation, and that's fine. That's what we want. We want each minimum to know only operations inside this segment. If we have some operations above, we just don't care about them. We will take care of them later. When we need, we will take care of these operations. Okay. Should I write the code? Well, let's write the code. So how to calculate minimum? Where is this? So when you add something to the segment, you make the same recursive procedure. So you start from the root. If it is completely outside, you do nothing. If it is inside, you make the following. So we need this we need two values. We need these two values. So when you stop in some node, you apply your operation to this number and also to this number. So you change this operation and also recalculate the current minimum. Yeah? So we need two numbers. Let's have this add number. So this add number in node X will be increased by V, and also this minimum in node X will be increased by V. So we take both these numbers and increase both numbers by V. Then return. If it is not completely inside, not completely outside, then we make two recursive calls like before. We make two recursive calls, and when we go back from the recursion, we recalculate the value in this node. To recalculate value in this node, we just say that the minimum in node X will be equal to minimum of two minimums to minimum in node to X plus 1 and node to X plus 2. And also, if you don't have this propagation, you need to apply the operation add. Like this. Also, you can apply propagation in the same way. We can do the same propagate operation. So what happens when you make propagation? You like move this operation to both children. When you move this operation to both children, you need to change this red value, like to calculate this operation. New operation that combine these two operations into one. And also you need to recalculate these two minimums. Because these minimums are now, before we had this minimum without this operation. Now when we move it down here, we need to calculate a new minimum considering this operation. So we just apply this operation to these two values, like perform what operation we need to perform, and also use the same value to modify these two minimums. Makes sense? That's all. That's how you propagate. Yes, and if you have propagation, actually the code became even easier because when you have propagation, you guarantee that all nodes from this node to the root are empty. So when you use propagation here, this add actually is 0. So you can remove this add. Propagate should be inside second if I think. Inside what second? No, you can move this propagate to the beginning of this function, but you should be careful because you can't propagate from the leaf node. So if you are in the leaf node, it has no children, so you can't propagate. So you can move this propagation to the beginning of this function, and then inside this propagation, check that current node is not the leaf of the tree. Because you will have some integer out of bounds exception, or something like, or null pointer exception, depends on how you implement. Okay? Now, the code is very simple. Again, you can watch a lesson on Edu if you are interested about implementation. In Edu, I have a special video where I implement all this from scratch, like in a few minutes. It's actually not hard to implement. No. Important stuff. What other operations can you use instead of these two operations? Let's try to have some abstract operation again. Some abstract operation. So we need some two operations. First operation we use when we apply function. So let's say something like modify from L to R V. We have this AI and then apply operation V. And calculate from L to R. This operation will calculate some operation on this segment. So it will be like LL. What operation we used? Something like that, right? So we have some operation here, L plus 1, some operation, and so on. Minus 1. No? So we have two special operations. We have one operation we use when we change node, change the element, and another operation we use when we calculate something. These two operations. Now let's check what properties do we need from these operations. No, first of all, we need all the properties from the previous lectures. So this operation should be associative. This operation also need to be associative. Just by the same reasons as before. Yeah? But there is one more interesting property we need to have to maintain all this data structure. Let's see what's going on. This property is very interesting. So we need to be able to recalculate the function when we apply when we apply operation to the whole segment. We need to be able to recalculate the function. So like here, when we apply this plus 5 to this segment, we just take the previous minimum, add the 5 to this minimum, and get the new minimum. So when we do this, we use the fact that when you calculate minimum of like x plus v and y plus v, it is the same as take previous minimum and then make plus v. Or in terms of these abstract operations, we need the following. So if we take some element x and then apply operation v, and take the sum of this and y with applied operation v. So if we apply operation to x and apply operation to v, then calculate the result. It must be the same as if we just calculate the result of this and then apply v to this result. Yeah. That's the property we need, and this is distributivity. So when you have two operations, they need to be both to be associative, but also they should be distributive to each other. So you cannot take some separate two functions and just apply it to the segment tree. You need these functions to be good working with each other. So it's like one function should complete another function. That's what you need. So we need these two functions to be distributive. Good. For example, minimum and plus are distributive. For example, sum and product are distributive. So if you calculate, if you have this plus operation and multiply operation, you have the same thing here. For example, some strange operations are minimum and minimum distributive, maximum and maximum. You have bitwise OR and bitwise AND, perfect distributive operations, and so on. So some pairs of operations are good. If your pair of operation is not good, you kind of need to think about what's going on. So maybe you need to change your operations a little bit, just to tweak a little bit, just to make them distributive. Or maybe you should add some additional parameters to your function to make them distributive. Sometimes that's what you want to do. But basically what you need to do to make some distributive operations. Cool. Good. So that's all the basic stuff I want to discuss. I want to talk some more about. Do you have some more time? I want to talk about some additional problems about segment trees. Yeah, unfortunately I spent too much time on this, but I think it's fine. We can spend another like 20 minutes on some problems. Let's talk about some interesting problems when you need to use some special segment trees. We'll discuss some problems in the home task discussion, but I want to have some more problems. Now, these problems won't be in the home task. This is just since we were talking about some interesting stuff, so let's try. Let's do. The problem I want to discuss is the following. Let's have some array, and you have a number of segments. You have some segments. I like this. So you are given some array and a list of different segments. And what I want to do, I want to calculate for each segment the number of unique elements on this segment. Number of, what's the difference? Elements on each segment. So you have all these segments in one. So you have the list of segments, and you need to answer to all these questions. So for each segment, you need to output a number, which is number of different elements in this segment. That's the problem. So there are different approaches how to solve this problem, and I want to discuss one of them. Lazy propagation. We always talk about lazy propagation like half an hour ago. Let's go. So let's have some array. Let's have some array like 5, 1, 3. Let's have another 1, and then another 3, then have 2, and 5 again, 1. And so on. So this is array A. And you have some segments of this array. So you have some segment here, some segment here, segment here, So you have a lot of different segments. And for each segment, you need to output the result of number of different elements on this segment. Go. So how to do it? Let's go. Let's start by the home. Let's try to answer all the queries of the segments which starts in the leftmost element of this array. So let's find all the segments which start in the first element of this array. So we find all the segments like this, where L equal to 0. So let's find all these segments. Now, how to answer this query? It's pretty simple. We need to find the number of unique elements on this segment. So to answer a query, we will just mark all the unique elements. And since the left border is here, we will just mark all the leftmost elements of each kind. So for each element, we will mark the leftmost element equal to this value. Yeah? So for example, for these 5s, so this we need to mark this element. This is leftmost 5. This is the leftmost 1. This is the leftmost 3. We don't need this. We don't need this. We need these 2, and so on. So these are the leftmost elements for each value. So to calculate the number of different elements on some prefix, we just need to calculate the sum in this array. Yeah. So if you create another array, like you put 1s in these positions and 0s in these positions, then to answer this query, you just need to have this prefix and calculate the sum on this prefix. This sum on this prefix will be equal to the number of different elements in this segment. That's the plan. Now, is it clear enough? Okay, I hope it's clear enough. Now we answer all the queries which starts in the leftmost element. Now let's move to the next query. So let's move to all the queries which start in the second element of this array. So let's find all the segment like these segments. So let's now let's find all the segments when left border equal to 1. Again, then left border equal to 1, we need for each segment to calculate the number of unique elements on this segment. So let's find all the unique elements. For each element, we find the leftmost position when we have this element. But this 5 is not inside this segment anymore. Yeah. So this 5 is outside of this scope. So we need to remove this 5. So this 5 is not the leftmost element anymore, because this 5 is outside of this segment. So we remove this 5. Now we find the next equal element. So we find the next element 5. And now this element is the leftmost element inside our segment. So we take this 5 and add it as the leftmost element. That's all. Now again, in this array, we mark all the elements which are leftmost element inside our segment. Makes sense? So we can answer all these queries. For each query, we just calculate the sum on this segment. This sum will be equal to the number of these unique elements, because we just put 1s in position when we have these unique elements. And so on. Now again, we move to the next position. So we move to the next position. We need to remove this 1. So we remove this 1. Find the next element equal to 1. Mark this element. And so on. So each time we do the following. We answer all the queries with this left border. And now we move the left border. When we move the left border, we remove this element, find the next equal element, and add this element. That's all. So how to make these operations? No, again, we need some data structure which allows us to remove element, to add element, and to find the sum on the segment. This is perfectly done with segment trees. You can do it with segment trees. So we will maintain these arrays of ones and zeros in the segment tree. Each time we will take all queries with this left border, calculate the sum of the segments, answer this query, then move the left border here. To move the left border, we just remove this element, find the next element, add this element. So we update segment tree here, update segment tree here, and move the left border. That's all. So on each step we have 2 updates of the segment tree, and for each query we need to find sum in the segment tree. So total time complexity will be the following. So we need to, for each query, so if we have m queries, so let's have n elements and m queries. So for each query we need to make request to the segment tree, so it goes to log n time. And n times we move the left border. So each time we remove the left border, we need to remove something, add something, it goes to log n time. So it is n log n. So this is the total time complexity. Clear enough? Any questions by now? You forgot how to use this chat. You need to write it, everything is clear just every 30 seconds. So if you don't do it, I'll try to explain everything once. Time complexity once again. Okay, let's describe the complexity. That's fine. Let's look on this time complexity. So what are we doing? So we take, every time we fix the left border. So we take all segments with left border equal to, so all these segments li equal to 0. Here are all segments with li equal to 1. We can split all the segments in these buckets in linear time. Yeah, we just iterate over all segments, make these buckets of segments, take the segment, put it in one of these buckets. You can do it in linear time. Now you take all the segments from this bucket, so you take all segments with left border here. Calculate the sum on this segment. It costs you log n time. You just make operation in segment tree. It costs you log n time. So for each segment, you will call one operation in segment tree. It costs you log n time. So these are operations. This you calculate sum in the segment tree. You do it once for each segment. And now you move to the next position. So when you move to the next position, you need to update segment tree here, update segment tree here. So you make 2 updates in the segment tree. Each update costs you log n time. So when you move the border of left border of the segment, you need to make 2 updates. 2 updates of the segment tree. It costs you log n time. So that's all you need. Also, you need to calculate the next element in the array which is equal to your element. So for each element, you need to pre-calculate the next equal element. So you need to pre-calculate these pointers. Yeah, but you can do it in linear time as well. I'll just leave you it as an exercise. For each element, you need to pre-calculate the next element of the same value. You can do it just going from right to left in linear time using hash maps. Perfectly. Okay, I'll just. That's all. Is it clear now? Now, what I want to do, what I want to do, I want to be able to answer these queries in any order. So in this algorithm, I use that I have all these segments, like it's an offline problem. So I have all these queries, and I just answer them in different order. Yeah. So I first answer all the queries when left border is here, then I answer all these queries, then I answer all these queries. And sometimes you have these queries come one by one. So you have not this list of queries, but you have like function, and you need to be able to answer the queries in real time. So you have some segment, and you need for this segment to answer the query. So what you can do? Again, you have some online problems. So you have online problem, then you have some query, some calc on segment from L to R, and this function should return the number of different elements on segment. And here you can just save this order and answer it later. You need to just return the result right now. So how can you do it? Pretty simple. So what we need to do is, let's see, what we need to do is to remember the state of this algorithm. Like imagine if you have these segments before. So in this algorithm, you kind of have some states. So first you have this state of your data structure. So let's see. I need to remove this. Need to remove this. So first you have this segment tree, right? So if this L equals to 0, you need this segment tree to answer this query. So if L equals to 0, you take this segment tree, get the sum in this segment tree, and this will be your value. Then we remove this 5, add this 5, so we have this segment tree. So if L equals to 0, you need this segment tree. If L equals to 1, you need this segment tree, right? If L equals to 2, you need to remove this element and add this element, and so on. Then you remove this, you add this. If L equals to 4, so let me remove this, add this, and so on. Sorry, I need to stop at some point. No. And so on. So now, depending on the value of this L, you need to take one of these segment trees and call the sum function in this segment tree. Let's have an array of these segment trees. So let's save all the states of this segment tree. Now we will have the state of segment tree in position L and call the sum function in this segment tree. So what we need is an array of segment trees. For each state, we will have a segment tree. Now, when we need to calculate the value on some segment, you're given some segment. You're given let's say this segment, and you need to calculate the number of different elements in this segment. So you see that left border is here, so you need this state of the segment tree. you take this state of the segment tree, calculate sum on this segment, and sum on this segment will be equal to the number of different elements of the segment. Good? Good enough. Yeah. Again, you stop to post that everything is clear. I'm kind of nervous. I'm very nervous when you don't write then everything is clear. Okay, maybe it's too long lecture. Okay. Okay, that's the last problem we discussed. Let's just keep it for a few more minutes. It will be over pretty soon. Yeah. Now everything is pretty cool, but we need to maintain all the states of this segment tree, and the total size of all the segment tree is n squared. Yeah. So if you just maintain all these states, the total size will be, so you need n states. For each state, you need to maintain this segment tree. So total size of all this segment tree is n squared. We cannot just maintain n squared memory. It's too big. So what we'll do? We will use persistent segment trees, like we discussed in the previous lecture. So what we can do is maintain this segment tree as a persistent segment tree. So we will make this first segment tree. Then we will apply these operations. So every time we move from this state to this state, we apply only two operations. So we apply this operation, we apply this operation. Then we have the new version of this segment tree. Then again, we take this version of segment tree, apply two operations. So we apply this operation, apply this operation, and get the next version of this segment tree. And if we use persistent segment tree, like on previous lecture, then we can have all these versions of the segment tree in one big data structure. And the total size of this big data structure will be just n log n, because each time when you make operation in persistent segment tree, you create log n new nodes. So each time you move from here to here, you create a log n new nodes in your persistent segment tree. So the total size, so if you use persistent segment tree, then the total size will be n log n. That's all. So how you create this again? You start from this. You create this. You create this state of 0 just by adding these ones into these positions. And something. Then you iterate for all I from 0 to n minus 1. Then you create new state using a plus 1, just by taking the previous state and applying these two operations, like set something to 0 and set something to 1. No, something, you mean you set I to 0 and you set next of I to 1. So if you use persistent data structures, you can just apply this operation and get the new version of this data structure. And you didn't break the previous version. Oh. Not too many of them. Let's have 4. Let's have 8 elements. Oh. I'll just repeat the same process from the previous lecture. So in the beginning, I have this array. So I have this segment tree 1, 1, 1, 0, 0, 1, 0, 0. So I build this segment tree for some. This is the segment tree for this first state. Yeah? So this is for L equal to 0, I have this segment tree. Now I need to change this element to 0 and this element to 1. So I use it, I just do it in persistent way. I change this element to 0, but I also maintain two versions of this node, this previous version and new version. And I change this node to 1. This node, yes, this node to 1. So for this node, I also have two versions. First version is 0, second version is 1. And now I just create all the top nodes. So here I need to have this node. So I clone this node to the new version. New version will have 1. I clone this node to 2 with these 2 leaves. I clone this to 1. I clone this to 2. And I clone this to 4 again. And now I have both versions of this segment. So when I need this first version, I just call my recursive function from this root. And when I need the second version, I call the same function but from this root. So I have different results in this segment tree or in this segment tree. Okay? And so on. And then you apply next operations, get the second version, and so on. And so on. Then you calculate all these versions. Each time you go to the next version, you create log n new nodes in your segment tree. So total number of nodes in all these versions will be n log n. That's all. Now, that's basically one of the applications of the persistent data structures. So why you may want to use some persistent segment trees, for example, is when you have something like this. So you have some segment tree, and when you need to answer a query, you need to find one of these previous states of your segment tree. So you just remember all the states of your segment tree in persistent segment tree. And when you learn you need to find some previous state, you just find this state in your array of segment trees and use this state to calculate your result. Cool. Okay, I think it's enough for today.